Welcome back, everyone. So we're in part 2 of our log notes. We're going to look at these remaining examples. So first problem we've got here is number 4. So it says find the point where the tangent line to the curve y equals e to the negative x is perpendicular to the line negative 2x plus y equals 8. So let's go ahead and figure out what our perpendicular slope is going to be first. So we'll get y is equal to 2x plus 8. So our perpendicular slope is going to be negative 1/2. So then on our curve, we've got y prime is equal to negative e to the negative x, which is equal to negative 1/2. So we'll get e to the negative x equals 1/2. We can take the natural log of both sides. So we'll get negative x is equal to the natural log of 1/2. And the natural log of 1/2 we could actually rewrite as the natural log of 1 minus the natural log of 2. So we can avoid the fractions if we want to. You don't have to, but you can if you want to. So note natural log of 1 is just 0, so we'll get negative natural log of 2. So x is equal to the natural log of 2. So that means that our slope is going to be perpendicular when x is the natural log of 2. So plugging that into our equation, we'll get y is equal to e to the negative natural log of 2, which we can then bring up the negative exponent, so it'll be 2 to the negative 1, which means y is going to equal 1/2. So then our tangent line is going to be y minus 1/2 equals negative 1/2 x minus the natural log of 2. And then we can multiply that out if we wanted to. All right, so moving on, we've got number 5 here. It says find the volume of the solid generated by rotating the region under the curve. Y is equal to 1 over x squared plus 1. From x is between 0 and 3, about the y-axis. So 1 over x squared plus 1. That is going to look like this. And we're only interested between 0 and 3. So we're really just looking at this region here. We're rotating about the y-axis. So then our volume is going to equal 2 pi. So again, we can use the shell method here. We can use x as our radius, so we'll have the integral from 0 to 3 times 2 pi x times 1 over x squared plus 1 dx. So then we can clean this up a bit. So bring the 2 pi out, and then we'll actually write the x maybe in the top here. So we don't have a natural log to start with, but clearly we're going to have to use a u substitution, and it seems like that's where our logarithm is going to come from. So if we let u equal x squared plus 1, du is equal to 2x dx, which means 1/2 du is equal to x dx. So x dx is going to be substitutable, but we also need to change our limits. So if x is equal to 0, u is equal to 1. And if x is equal to 3, u is equal to 10. So now these are our x values. So we're going to end up with the integral from 1 to 10 of 1/2 du over u. Now the half we can cancel with the 2. So we'll end up with pi, and then du over u is just going to be the natural log of u from 1 to 10. So we'll get pi natural log of 10 minus pi times the natural log of 1, but the natural log of 1 is 0. So natural log of 10 times pi, or pi natural log of 10, will be our final answer. And again, those are our new limits of integration up on top there. So that's equals u and u. So don't forget to change those limits of integration, and that's what we end up with. All right, so number 6, we're going to do some inverse work here, it looks like. So we are going to define h as the inverse function. So then h prime of e is going to be asking us when f of x is equal to e. So if we set e equal to e to the x plus ln of x, pretty obvious that this is going to mean that x is equal to 1. So then the derivative, f inverse prime of e, is going to equal 1 over f prime of f inverse of e, which is going to equal 1 over f prime of 1. So let's go back to our function here. So we'll note f prime of x is equal to e to the x plus 1 over, x. So f prime of 1 is equal to e plus 1. So we'll get 1 over e plus 1 using that inverse derivative. All right, so number 7, if a rectangle has its base on the x-axis and 2 vertices on the curve e to the negative x squared, show that the rectangle has the largest possible area when the 2 vertices are at the points of inflection of the curve. All right, so for this one, it's going to take a little bit longer, so I think we'll pause here actually. We'll come back to it, so we've just worked through those first 2 examples. So we'll come back to number 7 next time and finish that, and then work on our remaining integrals below here. All right, so again, shoot me an email if you have questions on the previous examples that we've looked at, or come by the office hours. Otherwise, until I see you again.